It's time to do part C for process dynamics and controls homework 2. So we're going to switch into something a little bit different than what we did most recently. We're going to take a look at the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. So we will derive that, kind of express that in an algebraic equation, and then we will simulate, as per usual, we will simulate this and discuss what we're seeing and why we're seeing it. So first I'm going to get into that derivation. I wrote our first part right here to derive the time-dependent heat diffusion equation for a uniform linear bar, as I said, assuming constant thermal diffusivity. So right here is our bar. I just went ahead and did that already, and so we want to derive this equation. Our energy balance is going to look something like this. The change in energy over the change in time. We can also say that this is equal to the density times the area times the delta x. So if we had this be like a delta x, for example, the heat capacity of this object, and multiply that by the change in temperature over the change in time. We also know Fourier's law. I should also mention that this Q is heat flux. So in the past, I've been using Q as a volumetric flow rate, but this is heat flux. So we'll have different units, and it's basically describing how heat moves in or out or through the system itself. So for Fourier's law, we have the heat flux is equal to K, which this is the material's conductivity, thermal conductivity, K times A times dt dx. So how the temperature changes as you're, in this example, moving across the bar. Taking from our energy balance, also just another reminder that this Q is heat flux, not volumetric flow rate. So taking from that equation, from the energy balance, we can write Qx. This will be our in, and then minus Qx plus delta x. This would be, for example, our x, and then if we were trying to look at what happens as we move to this new x value, which is x plus delta x, this right here being delta x. That's kind of what we're saying. We're looking at the in right here, out right there, just for, I guess, an example. And then we take what we wrote over here and set that equal and what we want to do is divide by a delta x on each side. Oops. Our goal is to isolate this term so that we can derive the time-dependent heat diffusion equation. we're looking at how the temperature changes with time. And then if we take the limit as the delta x approaches 0, so we're basically saying as this delta x is closer and closer to being 0, we'll have a negative 1 over a multiplied by the change in heat flux over the change in x, so the change in position, times the density times the heat capacity again, times this side stays the same. This side is the one that changes. This will always be a very, very, very small negative number. And simplifying that further, this q can actually be taken out. So I'll just keep drawing these arrows to show my steps changing. And up here with Fourier's law, we said that the heat flux is equal to Ka dt dx. Then we have the same right-hand side of our equation. And sorry, this should be a negative right there. And we finally simplify it, I believe, one more time, or actually a couple more times. We have 1 over a, and we're multiplying by a, so the areas cancel out. These areas cancel. We see we have x twice, and that would simplify to the second derivative. Down there. Don't forget that this is multiplied by k. And then we have the same right-hand side once again. As we said above, we are assuming constant thermal diffusivity. Thermal diffusivity. It's this alpha value right here, and it's defined as K divided by rho Cp. As we see here, we can divide by rho Cp. This would be our thermal diffusivity, and we can then simplify our final equation, where we have the thermal diffusivity multiplied by the second derivative is equal to how the temperature changes with time. That is our equation that we will be going off of for the, I believe, majority of this video, or all of this video. So we want to simplify this so that we can kind of put it into code easily and be able to graph things more easily. What we want to do is express this equation above, so the equation right above it, but as an algebraic equation using explicit differencing. We'll be using the finite difference method, which is an explicit method. And I'll get into why this is important to mention in, I believe, the next part of this homework, part D, but we'll stick with this for now. And then to define some things and just make it easier to understand, I'm going to write out some of the variables I'll be using. So I'll have a Ti, for example, Ti to the n. This is the temperature at spatial node I and time step n. delta x is the spatial step size, and delta t is the time step size. So if we look at a like more simplified kind of bar, I'm not going to really make it like super detailed or anything, but we have a bar, a straight bar that we're dealing with, and we are looking at, for example, we could look at these different spots in it, pretend that these are equally sized. We could call this one I. As I said above, I is the spatial node, and to the left we have I minus 1, we have I minus 2, etc., but with positive in the right direction. So what we want to do is we're going to say this the temperature change over the time change is roughly equal to this temperature at n plus 1 subtracting the temperature at n and dividing all of that by the change in time. So n plus 1 is the next spatial node, and n is the current node. We're also going to say something about this second derivative. That is roughly equal to t to the I plus 1 minus 2ti to the n minus ti minus 1 to the n power as well. And we're dividing it this time by this delta x squared. And this is basically simplifying how our temperature is changing. These two are different, these numerators are different from each other due to one being a first derivative and the other being a second derivative. And as I said, we have spatially, this is the spot to the left and the spot to the right. So what we get instead is we have this nice long equation where we have the thermal diffusivity multiplied by this entire term on the right now. And this equals this right up here. And we are going to solve this specifically for ti to the n plus 1. So we're solving for the next time step, the following time step. If we know our current temperature at this time, what we're looking at now is what is the temperature after this delta t occurs. And that right there comes from here. So what we need to do is multiply by this delta t and add this ti to the n plus this thermal diffusivity this thermal diffusivity divided by delta t. I was right. The thermal diffusivity multiplied by delta t divided by delta x squared, and then multiplied by the ti plus 1 to the n minus 2 ti to the n minus ti minus 1 to the n. So what this does is this solves for a future temperature after some time has passed. So yeah, what we've done so far is we derived the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. We also just expressed the heat diffusion equation from part C1 as an algebraic equation via explicit differencing. And instead of going into the code right now, I'm going to jump ahead to this fourth part just so that I can do everything on my iPad first and then I'll get into the code. But essentially, we're looking at this von Neumann stability analysis to explain why simulation results are unstable when R is set larger than 0.5, and I'll go over what this R value is. But when I do make the code, we'll simulate the results for R is just under, at, or just over 0.5, and that'll kind of highlight why the graph looks the way it does, I should say. Like I said, jumping ahead, we will get into the code after this. Looking at the von Neumann stability analysis, why are simulation results unstable when R is greater than or equal to 0.5? So we know that for this simulation to be stable, the wave function must not grow indefinitely. If that grows indefinitely, then we will have our instability and probably oscillations, or divergence, I should say. So it's essentially this equation that we have above, except we're setting this R value that I just mentioned. I'll put this in a different color. I'll put it in green. R is equal to the thermal diffusivity times the time step change over the position change squared, and we're doing that just for the ease of being able to write this out because all of these would be constant values. You would have some material with a constant thermal diffusivity, so you would have a number here. This would be some time step, a number that you would define, and you would also define the delta x. So this would be some number, and we are calling that R, just for some simplification. And then we can rewrite this out as ti to the n plus 1 is equal to ti to the n plus R times ti plus 1 to the n minus 2ti to the n minus ti minus 1 to the n. So another way we can kind of write this as a wave function, and I won't go too much into where this comes from, but I will basically be getting rid of these I plus 1, I minus 1, or basically these entire terms, and replacing them with exponential terms. So then this simplifies, or I guess not simplifies, but we can also write this as ti to the n plus r, so that stays the same. I'm going to pull out a ti to the n from here. We're pulling that out of the parentheses. And then what ends up staying, inside the parentheses, we have e to the I, k, delta x. Again, I'm not going to explain exactly where that those Euler numbers come from. Minus 2. And then plus, we're adding e to the, but it's to the negative I, k, delta x. Something we want to recall just for some simplifications that we're about to do. We have Euler. We know that e to the ix plus e to the negative ix is another way that we can write cosine of x. And I actually wrote something wrong right here. This should be a 2 cosine x. So when we go ahead and simplify things, we still have ti to the n plus 1 is equal to ti to the n plus rti to the n times 2 cosine delta x minus 2 ti to the n. And noticing we have a lot of ti to the n values, we can simplify it further. We're going to say ti to the n plus 1 is equal to ti to the n times 1 plus r. So the 1 gives us that value, the plus r gives us that value. Multiply this by 2 cosine delta x minus 2. That's how we get the 2ti to the n. And we need our amplification factor to be less than or equal to 1. We therefore need the absolute value of this term right here to be less than or equal to 1. Essentially, this value is what determines how the next time slot, how the temperature behaves there is compared to the previous spot we were at before. If that is too large, then this will not be stable. And what we want to find basically is to solve for this right here and find what R value will cause the instability. So I'll write this as -1 is less than 1 plus R times 2 cosine delta x minus 2. That is what I said with these absolute value signs. I just rewrote it down there like that. Subtracting this 1, we then get -2 is less than this whole R term, 0 on the right-hand side. I'm also going to go ahead and pull out this 2 and put it with the R so that we have the cosine term by itself. And as I'm going through this, I also realized another thing I forgot was we're putting in, this should be 2 cosine times k. So all of these should have our k value associated. So instead of rewriting that, I'm going to indicate that right there. And something we know is that cosine goes from a value of -1 to +1, and it never exceeds those. And since I pulled that 2 out, I meant to write a 1 here. I think I caught all of my mistakes, hopefully. So the lowest that this can be is -1 minus 1. Write that down here. I'll divide by -4. And once again, one more thing that I forgot was these should all be less than or equal to, not less than. When we divide by that -4, we have to flip our sign. So what we are saying is r must be less than or equal to 1/2 or 0.5, which we have in our question, why are simulation results unstable when r is greater than or equal to 0.5? As we can see here, when r is not less than or equal to 0.5, we get the instability with our wave function. And as I said, it's worth mentioning, with -1 being the minimum, we could also say that the maximum value that this cosine k delta x value could be is +1. And if this is +1, then we would have 0 in the center. 0 is always going to be equal to 0, so we would not have a problem there. But when this cosine value is at its minimum, that is why r must be less than or equal to 0.5. To wrap that up, what I'm mainly trying to get across is when r, remember this r is the thermal diffusivity times the time step divided by the spatial step squared. When that's greater than 0.5, the amplification factor, this is not true anymore. And any error within the system grows exponentially. So you will get divergences, you will get extreme, just general instability within the graph. And that's kind of why I wanted to do this part first, and to also get my writing out of the way, so that now I can just go into the code and it'll make more sense why the graph looks the way it does when I'm at a value a little bit below 1/2 for r versus above 1/2 for r. And I'm going to get into the code now. But yeah, what we're doing right here is we're going to simulate the time-dependent response of a uniform bar. It's a linear bar, assuming constant thermal diffusivity, and the entire bar is initially at 20 degrees Celsius, but then its ends are raised and then maintained throughout the simulation to 40 degrees Celsius and 100 degrees Celsius. So the left will be 40 degrees and the right will be 100 degrees. And what we're doing is simulating how the heat diffuses throughout this bar over time. And as I highlighted, this is our R value, the thermal diffusivity times delta T over delta X squared. And we already did this part, so I'm going to touch on once more why it's unstable when R is greater than 0.5. Let's set our R value equal to 0.5 just for now. And our N is the spatial nodes that we have across our bar. We're going to use 50 just for now. We're going to set an array of temperatures where it is size N and all of them are equal to 20. That's because when it's at steady state, before any heating occurs on the ends, every part of this bar is at 20 degrees Celsius. Then when things change, we want to say at the leftmost node, which is index of 0 in this case, we're going to set that equal to 40 degrees Celsius. And then T minus 1 is the last node, and I believe we're setting that to 100 degrees Celsius. Don't know why it keeps wanting me to do that. And then we're going to make an array for the x-axis. There we go. Size N. As always, make subplots. Now we'll add a scatter with x being our x-axis. y being our temperature values. And this is at our time is equal to 0. That's our scatter for that. For n in range, let's go for 1,000 right now. This is kind of what I wrote out earlier, but we're saying from the second part, so not the 40-degree end, but the piece right next to it, from there until the penultimate spot, because again, we don't want to be changing the index of 0 or the final, because they should be set at 40 and 100 degrees respectively throughout the simulation. Set this equal to T plus R multiplied by this T subtract 2 times T. I'll just copy and paste that. Minus, or sorry, I believe it's plus T. There we go. So for each node, this actually should be, I don't know if I was correct earlier, but this should be the right-hand node. So to the right of the current node. This should be to the left. I'll update the layout. I think that title might be too long, but we'll see what happens. Let's see what it gives me here. So the x-axis is the node, or the position along bar. The y-axis is the temperature, so that is correct. I'm just going to put in degrees Celsius. The legend title should be the time step. And I'll set a width and a height. And I'll set my usual template. I just paused so I could clean this up really quickly so that it was hopefully more visible. And then something else, I completely forgot to add a scatter. So we want a scatter to be adding as we're going through this for loop, or else we will simply just have this scatter right here. So let's see if what it wanted me to add was correct. The x again is the x-axis, y is the temperature. We can do the mode as lines, set the name as a function, and the time is going to be equal to n+1. And let's see what this looks like. Does it show? I think it might be. Okay, and this will kind of explain why I just forgot to add this. As you can see, there's a lot going on here, almost just too much for us to see. But what we can see is we set the left-hand side and the right-hand side of our bar to the correct temperatures, because the whole time this left bar is at 40 and the rightmost one is at 100. And the reason I forgot about plotting this scatter was because before I put this under an if statement, And we are going to be using the modulus. So this is this percentage sign. Sorry, the percentage sign is the modulus. So what we're saying, I think 100 might be a little too high. So we're saying if n is divisible, perfectly divisible by 50, so that means no, so it's a multiple of 50. If that's true, then we add the scatter. And if that isn't true, it will just keep running the code until it is. And the point of that is that we will not have, we won't have that problem. There won't be too many lines. And since I'm doing that, I might increase this value a little bit more. That was a lot more. Okay. It looks good. Okay. This time we can actually follow it, and as you can see, it's going up by 50 every time. At the immediate start, when the very left and very right of this bar were heated, most of the bar was still at 20, because after barely like any time, 0 time has passed, it doesn't have a lot of time to diffuse. And then as we get to later times, that's too far. As we get to later times, you can see how it behaves, how the temperature profile behaves throughout this one-dimensional simplification of a bar. Obviously, it's going to heat quicker on the right side because 100 degrees is a lot hotter than 40 degrees. And let me try to find more of an in-between. It seems like there's a little bit of a bend. Okay, there's some bends in that one. But once you get to this final time, it's completely straight and no longer curved. And then you get these beautiful lines. Now, earlier I made a big fuss about this R value. Right now, we have it set to 0.5. I'm gonna set it really low just so you can see that it does not have a big impact. It slightly changes because our time step, as that's decreasing, our time step is smaller. So we do get more lines, but again, that could be fixed with this modulus. So that's not a big deal. First thing it wants me to do is 0.499. As I said, this graph looks great. And this is when we have R set to 0.5. What we calculated by doing part 4 earlier was that R needed to be less than or equal to 1/2 in order for this simulation to be stable due to just the setup, the pure setup of it. And if I set that to 0.499, we don't have any really noticeable difference at all. 0.4, again, no noticeable difference. So you're like, okay, if 0.499 wasn't very noticeable of a difference, what would 0.501 do? So this is only a little bit above 1/2, and immediately, look at this, 5 million degrees Celsius. Obviously that's not how this would behave. So it's going completely out of whack, completely diverging, oscillating like crazy. And look, if I just get rid of that one, it looks fine. add a lot of zeros and then a little 1 there. So there is some point, and that's probably just due to the error of the system itself, but there becomes a point where this will impact the graph. Looks like it's not quite sensitive enough to be impacted. Okay. I'm trying to find where it's on the cusp. Okay, this is pretty good. Not good as in acceptable, but this kind of shows, we can see the graph that we saw earlier, but then we also see the horrible graph we saw at 0.501 for the R. Let me see if I can get that a little closer. Yeah. And it happens along when this becomes more steady. We get this, which is obviously not intended. But yeah, I like looking at this one personally because you can really see how it becomes that graph that had the 5 million degrees Celsius. The ideal number for this is 0.5. That's going to give us our best values. And I'm going to skip on my usual end screen because I don't think it's quite necessary right now. But basically, in our next part, what we're going to do is express this equation that we calculated in the first part of part C in this video, but using Crank-Nicolson differencing. And the point of this is that the Crank-Nicolson differencing scheme is stable regardless of the choice for R, which is obviously a huge benefit. The main thing with this R is that R is equal to the thermal diffusivity multiplied by delta T over delta X squared. So if we want to use larger time steps, we need to have a larger R because they are directly related to each other. Otherwise, we would need a very, very different delta X. But if we want to raise the delta T, then our R value is going to need to be higher than 0.5, but what we have here is if we go above 0.5, it completely diverges and is unreadable. So that will be in part D. As always, thank you for watching.